Hello, Dr. Martell here again, and in this lecture I just want to go over the content of this symbolic logic course generally, and then get into the content of the first chapter of our textbook in particular. And that chapter has to do with atomic sentences, which are the basic building blocks of an artificial language that we're going to be learning. That language is FOL, right? An acronym that stands for first order logic. Okay, so first concern about course content generally. Symbolic logic courses such as ours typically serve as introduction to logic courses, right? And indeed, it's often the case that the only logic that people ever get in the course of their university studies, college studies, is symbolic logic. Logic generally is the science of reasoning, okay? And this science, among other things, identifies principles, rules, distinguishing good arguments from bad arguments, okay? And look, an argument is basically a process of giving evidence, right, in support of some claim or other. Okay? Another way of putting it, arguments, sort of in the context of logic, when we talk about arguments, we're talking about a bunch of statements, some of which are supposed to provide reasons for believing some other statement. Okay? The statements that give you reasons for believing something, those are called premises. That which you're supposed to believe based upon the premises, based upon the evidence, that's called the conclusion. Okay? This process of bringing forth evidence in support of a conclusion, that process is one that can go well or poorly, right? So there are good arguments, there are bad arguments. Turns out that the good arguments share certain features, bad arguments too share certain features. And of course, you all have been arguing probably for a very long time, since you were 5 years old, if not younger. You've learned how to do this well to some extent, and you've also learned to some extent what bad reasoning looks like. Okay, and you know that bad reasoning, right? There are lots of cases of it. Some of those cases kind of look alike, right? It's as though in the course of bad reasoning, errors are made, and different bad arguments can exemplify the same kind of error. So you know, for instance, if you want to argue that someone has said something false, or if you want to argue that someone else's argument is a bad argument, you probably already know that insulting the person, right, talking about all sorts of bad character traits they have, is really not a good way to go. Because after all, the fact that someone is a bad person does not imply that absolutely everything that they say is false, or that absolutely every argument that they give is a bad argument. Even bad people are capable on occasion of telling the truth or giving a good argument. So the mistake of attacking a person when trying to refute their view, that's a very common error in reasoning, and it's known by a Latin name. This error is called argumentum ad hominem. Okay, so that's an example of a very common error in reasoning. Okay? There are also very common ways of making good arguments. So suppose I wanted to establish that someone was unmarried. Well, I might bring forth the following evidence. So-and-so, that person, is a bachelor. Okay, and all bachelors are unmarried. there you go. I mean, that would be conclusive evidence that that person is unmarried. Or suppose I wanted to establish that someone is mortal. That means they will die. Well, I might persuasively argue, well support that claim by first pointing out that all men are mortal, and the person in question is a man. Okay. So hopefully what you can see there is that those are both good arguments. The arguments have something in common. Okay, you can probably already tell that what they have in common is a certain kind of pattern. Right? Turns out there are good making patterns in argument. One of the things that logicians have tried to do is identify those patterns, right, and distinguish them from bad patterns and other kinds of errors in reasoning. In this course, the symbolic logic course, we're going to be especially concerned with one especially important good-making feature of some arguments. And this good-making feature is called logical consequence. Okay? In some good arguments, the conclusion is a logical consequence of the premises. Okay. What the person giving the argument is trying to establish is a logical consequence of the evidence that they have brought forth. Okay? This is a good-making feature of some arguments. We want to try and get clear on what this amounts to, what logical consequence is. We also want to develop and learn to utilize techniques for establishing logical consequence. Techniques for establishing that a conclusion is a logical consequence of the premises. Okay. To learn these techniques, we're going to learn an artificial language. And that language, again, is first-order logic, or FOL. FOL is an artificial language that models logically relevant features of natural languages such as English. Okay? And what I mean by logically relevant feature is a feature of a language like English, right, that matters when it comes to whether an argument in English is a good argument or a bad argument. Okay, so that's what I mean by logically relevant features. And so what this language does is it sort of captures those features and abstracts away from other aspects of a language like English that are not relevant for whether the argument works or not, right? Whether in particular the conclusion is a logical consequence of the premises or not. Okay, now, the techniques that we're going to develop for establishing logical consequence, those techniques are techniques that you are going to be able to use, hopefully outside of the context of this class. I mean, hopefully you'll be able to take these techniques and employ them directly to arguments given in a natural language like English, right? You'll be able to employ these techniques to assess whether arguments given by other people are good, and you'll be also able to use these techniques to construct arguments of your own, especially if you're after arguments where the conclusion is a logical consequence of the premises. In this class, though, we're going to use we're going to become familiar with, right, versions of these techniques that apply in particular to FOL. Okay, so strictly speaking, we're going to be using these techniques to establish that arguments in this artificial language are such that their conclusions are logical consequences of their premises, or not. Right? Okay. So more about FOL now. First order logic is an artificial language mainly developed in the mid-19th century to early 20th centuries. First by Charles Sanders Peirce, I think it's Giuseppe Piano, and Gottlieb Frege, and then by Russell Whitehead and Ludwig Wittgenstein, among other 20th century figures. FOL was largely, anyway, developed in response to a crisis in 19th century mathematics. So as many of you know, the 19th century is a very important century in the very long history of mathematics, because there were a number of actually startling at the time new developments. So mathematicians over the centuries have been adding numbers to the numbers that they originally worked with. So originally among the Greeks, your numbers were like whole numbers and fractions, and then the Greeks eventually recognized what we call like irrational numbers too, like square root of 2 or pi. At some point, I think 0 got added, and we got like negative integers too. I believe it's the case in the 19th century that numbers that are called imaginary numbers, right, also became widely accepted among mathematicians. Additionally, as a result of I think Cantor's work in set theory, numbers called transfinite numbers were proposed and accepted among some mathematicians. And transfinite numbers, this notion has to do with the fact that there are many infinite sets of numbers. So like the whole numbers, starting with 1, that would be like an infinite, that'd be like a collection of numbers with like an infinite number of numbers, right? Integers, right, would be like another one, also infinite set. Real numbers, so like all the integers, right, plus numbers like square root of 2 and pi and so forth. That's another infinite set. It turns out that the set of reals is infinite, the set of whole numbers is infinite, and the set of reals is actually a bigger infinite set than the set of whole numbers. Right? I believe it's the case that there are sets too, at least in principle possible, that are bigger than the, also infinite, but also bigger than the set of reals. Okay, and so these infinite sets can be ordered by bigness, by largeness, right? And that's where we get the notion of I think transfinite numbers from. Also important, in the 19th century there were a number of new geometries developed. People for a great deal of time, probably since geometry began, thought that there was really only one geometry, and the fundamental principles of that geometry were captured by a fellow named Euclid, who was a Hellenistic age Greek geometer. One of the axioms in particular of Euclid's system, I believe, can be paraphrased as follows. That's for any straight line and a point, there's exactly one parallel line that can be drawn through that point. Okay. In the 19th century, it was discovered that you could develop a consistent system of geometry while rejecting that axiom. You could actually develop a consistent system of geometry by holding that there were no lines parallel through the point, or you could develop a consistent geometry by holding that there were actually an infinite number of parallel lines parallel to the first line through that point. And so we get in the 19th century to like non-Euclidean geometries. So many mathematicians in the 19th century didn't know quite what to make of these developments. Some were skeptical and didn't want to accept these new things. Others accepted them, but wanted to, for instance, imaginary numbers and transfinite numbers, wanted to classify them as somehow like second-class citizens in the city-state of mathematics. And so I think a mathematician named Kronecker held that God created the natural numbers, and all the others are works of man. Philosophers and mathematicians at this time got the idea that they could settle these disputes about, you know, what's legitimate mathematics and what is not, what of the new deserves inclusion, and what should be rejected, by first finding what they called the foundations of mathematics. And the foundations of mathematics would be sort of like the relatively few basic mathematical truths from which all the rest could be derived, right? And actually, to use language that we're going to develop in this course, these would be the few basic mathematical truths of which all the others are the logical consequences, either directly or indirectly. The idea is basically that we could use this to distinguish between legitimate mathematics and the illegitimate mathematics in the following way. If it's one of the basic truths, or if it derives from one of the basic truths, well, then it's in, right? It's that part of that's real mathematics. That's legitimate. And if it cannot be derived from the basic body of truths, well, that's out. Okay. A group of philosophers and mathematicians held furthermore, or thought furthermore, it was a hypothesis, that this foundational part of mathematics, it's actually logic. Like the fundamental mathematical truths are in fact logical truths. Okay. Now, logic is a very, very old discipline. It goes back at least to Aristotle, who is a 4th century BCE Greek. He was Plato's best student. So the discipline of logic was already thousands of years old, right? In the West, anyway, by the mid-19th century. Okay. These people, though, who were interested in identifying the logical truths, they're at the foundation of mathematics, supposedly. These people found that logic, as it had been handed down to them, from like Aristotle, was really not adequate to their purposes. Okay. After all, if they needed a bunch of logical truths that would serve as the basis for the whole rest of mathematics, they would need logical truths involving like rigorously defined concepts. Okay. Additionally, they found the need to introduce like specialized symbols, which are quite common within mathematics generally, as all of you know, and rules too for constructing well-formed expressions consisting of those symbols. Okay. So there was a need then to, I guess you could say, like mathematize logic. The result of this is the artificial language that we're going to be studying, and that's so-called first-order It was, for the most part, completely developed by the very beginning of the 20th century. I'm pretty sure a book by Russell and Whitehead called Principia Mathematica, I think published in what, 1901 or so. That's got at work within it um, pretty much, right, everything that is now considered first order logic. So there you have it. Okay. That project, it's called logicism. This project of identifying the foundations of mathematics in a number of, or finding the foundations of mathematics in a number of logical truths. That project failed. It failed, I believe even prior to the Second World War, like in the early 1930s, I believe that a mathematician and logician named Gödel was able to show that it had to fail. That what they were trying to do was impossible. They developed these figures, mathematicians, philosophers. They developed FOL as part of that project, right? Identifying the foundations of mathematics. The project failed. It was an impossible project. It had to fail. Okay? But ironically, right, FOL goes on to become hugely important anyway. Okay. Why? Well, one, it goes on to be hugely important within mathematics, and that's because as I understand this development. Okay, I'm not a mathematician. While the project of trying to find the foundations of mathematics was largely abandoned, that was given up. After all, it's impossible. The project of unifying mathematics went ahead. It went on. Okay, and I think one unifies different parts of mathematics when one discovers sort of one mathematical theory that allows you to make sense of, right, many other different branches. Okay. It's my understanding that set theory combined with this mathematical logic, FOL, it does that kind of unifying work. Okay? It's not the only proposed unifiers. There have been other proposals. I think one was what's called group theory, and a more recent alternative, I think, that's still being considered as something called category theory. But right, one very influential way of unifying the whole of mathematics is by way of something called set theory along with first order logic. And this means that really you have to know first order logic and set theory too to get much of anywhere in advanced mathematics these days. So I think it's simply essential to doing work in that field. FOL, though, turns out not to just be important in mathematics, but also to be important in a number of other sciences as well. And these are the sciences that our authors, Barwise and Etchemendy, call, for better or worse, the symbolic sciences. So FOL is also very important in linguistics. Right? And again, for a variety of reasons. I mean, one of them is this. FOL has actually a good deal of what's called expressive power, right? A surprising amount of what we want to say can be said in FOL, but it turns out to have actually much less expressive power than a natural language such as English, right? And so the comparison between what can be said in FOL and what can be said in English is very illuminating for people trying to understand, right, what a language like English can do and how it is able to do it. Additionally, there are people within linguistics who are still attempting to show how certain parts of speech are constructed out of simpler parts of speech. These more complex constructions, the hypothesis is they are built out of simpler expressions logically, and it's first order logic that these linguists turn to with some additions to try and show how it is that the more complex expressions are built out of the simpler expressions. Okay. FOL is also extremely influential in artificial intelligence because people working within that field, due to its great precision and surprising expressive power, they've thought that FOL was a good choice for encoding knowledge. Right? So an artificial intelligence needs to, in some sense, know certain things, right? To know these things, it has to be, in some sense, told these things, right? The language that's used to tell it, that's first order logic. And then finally, and perhaps most relevantly for most of the people taking this course, FOL has also been hugely influential within computer science. For one thing, as our authors point out, like all programming languages are in one way or another like inspired by the example of first order logic. Right? Again, an artificial language of great expressive power. Secondly, many of the notions that are employed commonly in various computer languages, they're taken over from first order logic. So I think the notion of like quantification, quantifiers, the notion of scope too, these are derived from first order logic. Finally, and I have to take the word of our authors on this point, there are some programming languages that just are FOL. Okay. So this is why the authors claim that FOL is the lingua franca, or common tongue, of the symbolic the symbolic sciences. This is the artificial language that workers within these diverse fields, all of them are proficient in to some extent. Okay, as a language, FOL has both a syntax and a semantics. Okay. Syntax, you can explain it a number of different ways. One way of explaining it is it has to do with intra-symbolic relationships, or the relationship of some symbols to other symbols. Okay. Specifically, as I put it in the slideshow, the syntax of FOL has to do with the rules according to which strings of symbols count as expressions of the language. Just to give you sort of a sense for what I'm getting at here, like I have regular dealings with a 5-year-old, and she has some of those magnetic letters that you can put on a refrigerator, like in strings, right, of symbols. And she'll sometimes arrange these letters and asks me, what does this say? and it's almost always the case that I have to tell her, that doesn't say anything. Right? I mean, she hasn't put together the symbols in such a way that the result could possibly say anything in English or any other language, for that matter. The rules that you have to abide by in order to actually say something, right? Those are rules of syntax. Okay? They're syntactical rules. An expression satisfying such rules is called a well-formed formula, or WOOF. Okay. In chapter 1 of our textbook, you are taught to construct the most primitive WOOFs of FOL. namely atomic sentences. And note, by primitive, I don't mean to be making a value judgment. Primitive here just means basic, right? As the name suggests, atomic sentences are kind of like basic meaningful units in FOL, out of which, right, more complex meaningful units, more complex sentences can be constructed. And by next week, we'll be getting into how those more complex sentences can be constructed. Okay. Atomic sentences are constructed out of names, which are also known as individual constants, predicates, and parentheses, at least in this dialect of FOL. Just an aside here, FOL is an artificial language that has a number of different, you could call them dialects, or maybe even you could say that there are a number of different cognate FOL languages. Okay, cognate languages are languages that are deriving from some one mother tongue. So like Italian, French, and Spanish, right, are cognate languages because they all derive from Latin. Right. You could say then that there are a number of different cognate FOL languages or a number of different FOL dialects because there have been a number of different systems consisting of symbols developed for doing the job that FOL was designed to do. And what I'm getting at here is that there are actually a number of different like functionally equivalent languages. They all count as FOL, but they use different symbols put together according to like different rules. Okay, so like you're going to be introduced in this course to one dialect of FOL in particular. To the credit of our authors, occasionally they will note, right, that both that there are other dialects and what these other dialects look like. Okay. They won't require you to study these other dialects, though. Time does not permit. So, in any case, atomic sentences are constructed out of names, predicates, and parentheses. Names are going to be lowercase letters of the English alphabet, and predicates are capitalized words or phrases of the English language in the version of FOL with which we're dealing. For example, cube with capitalized, right? Parenthesis, B, lowercase, parenthesis. Medium, parenthesis, B, lowercase, parenthesis, and left of, parenthesis, B, comma, D, parenthesis. Okay. Note that the predicate in the examples I just gave appears first, followed by some number of names in parentheses. Okay. Aside here, that is almost always the case, that the predicates appear first. There is at least one really important exception, and that's identity. Instead of writing it out, so capital I, D, and so forth, we use the equal symbol, okay, or in mathematics, like it could also be called like an identity symbol, right? That symbol, it's a predicate. It appears between two names, okay? So most of our predicates are going to be prefix. There are some exceptions. Identity is an exception. It's called an infix predicate rather than a prefix predicate. Infix because it goes in between, right? The names that it links. Okay. The number of names required to have a well-formed formula depends upon the predicate, with some taking only one name and others taking two or more. So cube B, that basically tells you that B is a cube, okay? Cube is called a unary predicate because it takes just one name, right? If you don't include a name, you don't have a well-formed formula. If you include two names after cube, you don't have a well-formed formula. If you were to put the name B in front of cube, you would not have a well-formed formula. If after cube you had four names, it would not be a well-formed formula. Cube is a unary predicate, so it takes one and only one name, and it must take one name if the result will be a well-formed formula. The number of names a predicate takes is its arity, right? So if someone asked me what is the arity of cube, I would say that's a unary predicate. Left of, on the other hand, is a binary predicate. It's called a binary predicate because it takes obviously like two names. Okay. Between takes three names, and so it's called it's a ternary. It's a ternary predicate. Okay. If I was asked what is the arity of between, I would say, well, that's a ternary predicate. Okay, FOL, as with any other language too, also has a semantics. Semantics has to do with meaning. Okay? So if syntax has to do with sort of intra-symbolic relations of symbols to symbols, okay? Semantics has to do with the relationship between symbols and, for lack of a better word, the world. Okay. In this first chapter of our book, you're also taught a bit about the semantics of FOL, or roughly the meaning of woofs of this language. I say roughly because getting clear on the meaning of a woof amounts to getting clear on the conditions on which it is true or false. Okay. Yeah, look, what I have in mind here is the fact that there are some expressions in English such that if you want to get clear on what they mean, it makes a lot of sense to ask what would make them true, right? Like the cat is on the mat is a famous example of this. Like, what does that mean? Like, well, if you want to teach someone what it means, right, you might get them to compare situations in which it is true with situations in which it is false, right? That's how you could get them clear on the meaning of the cat is on the mat. But what would you do if you wanted to get somebody clear on the meaning of hello? Right? Surely hello or welcome is also a meaningful expression. In spite of the fact that it's meaningful, though, it does not seem to have truth conditions. Right? There's no way the world is that makes it true, rather than false. Hello isn't something. It's not a part of speech that's true or false at all, though it is meaningful. Okay, and that's why I say that like roughly, right? If you want to get clear on the meaning of something, you need to get clear on the conditions on which it is true. This holds for some parts of a natural language like English, but not all parts. Okay, it does conveniently hold true, I think, for all, well, nearly all parts of FOL. All right. More on the semantics. A name, also known as an individual constant, always refers to some one object that is assumed to actually exist. Okay, so as our authors point out, right, this is rather like proper names in English. Like I think they give the example of like Matt. Okay, unlike the word dog, right? Matt refers to like just one individual. An important difference between names in FOL and names in ordinary everyday English is that names in English and other natural languages don't always refer to objects that actually exist. Right? So I think Pegasus would be a good example of a name in English, for something that does not actually exist. In FOL, we just basically screen those cases out. It's assumed that if we're using a name, right, that name refers to a unique individual that actually exists. Okay. Right. The meaning of an atomic statement, so it's going to consist of a predicate and an individual name, an individual constant or name. The meaning of an atomic statement amounts to the conditions on which that statement is true, and thus the conditions on which what is said about the named individual or individuals is true. Thus, getting clear on the meaning of between, BAC, is getting clear on how the world would have to be for it to be true that B is between A and C. Okay? And that is where Tarski's world comes in. It'll help you figure out how to interpret, get clear on the meaning of atomic sentences of the version of FOL with which we will mainly be working. Okay, so you're going to need to do a try it again. There's no need to submit your work to me, but it's important to do this to get familiar with the workings of this program, Tarski's world. And also just get used to constructing atomic sentences in FOL and get clear on what they mean. So what I have here on one of the later slides called Introduction to Tarski's World is a picture of what things look like when you go through the You Try It. And I believe it's opened up something called like Wittgenstein's World. And I think it's Wittgenstein's Sentences. Okay. The You Try It asks you to assess, just sort of on your own, maybe silently, each of the atomic sentences listed in the sentence box that are about the world depicted to the left. And the world is going to be a chess set. It's a chessboard. And on the chessboard are various kinds of I think they're platonic solids. These are three-dimensional geometrical figures, either a cube, an octahedron, or a tetrahedron. Okay, tetrahedrons have triangular sides. Cubes, have square sides. And I think the octahedron has 5 sides. Yeah, it looks like 5. Looks like 5 sides. Okay. Note, you can check your work here. Going through each sentence individually by first clicking next to that sentence, and then you'll see like there are buttons at the top of the Tarski's World window, located over the sentence box. They come in groups. There's a group of 4. There's a middle group of 3, and then to the far right there's a group of 2. That middle group of 3, the first one of them, it says T, I think in green, and then / F in red. If you click on that, that'll just tell you whether that sentence is true relative to the world that's depicted at the left. Okay, you can do this sentence by sentence, or another thing you can do, the box to the immediate right of that TF box, I think it has lots of little TFs, TF. That box, if you click on it, it'll tell you immediately for all of your sentences whether they are true or not relative to the world depicted to the left. Okay. The rest of the slides for this time sort of take you through the opening parts of doing the first of the homework exercises assigned for this week, and that exercise is exercise 1.2. So first you're going to open up Tarski's World, okay, and then what you'll do is you'll add in the sentence box the sentences that are listed for exercise 1.2. Okay, you're going to want to do that not by typing out by hand each individual symbol. It's best to use the buttons that are located right above where the sentences are going to appear. When you're done with the sentence, click Add After, right? Of course, if you made a mistake, you can use the delete button to delete. If you also forget to add one of the sentences because your eye wanders when you're looking at the page in our textbook, there's also an add before button, which is sometimes helpful. Okay. What those exercises are going to do is first just ask you to type in those sentences, save the sentence file, and submit it using submit. It's then in the very next exercise going to ask you to create a world in which all of those sentences are simultaneously true. Now, to create that world, what you're going to want to do is you're going to want to like first create figures, cube, tetrahedron, or octahedron in the world depicted on the on the left of the screen. The button right above the depiction of the world on the right of the screen, to the far left, if you click on that button, it'll drop down a figure. I think it starts out as a cube always, but then you can like select from the menu of figures, again located above the depiction of the world, and change it to a tetrahedron or an octahedron if you need to. You can use the letters right above those symbols to name the figure. You can also change the size of the figure using these buttons, and you can move the figure around the board by just I think clicking actually on the figure and then moving it right to wherever you like. If you want to get rid of the figure too, I believe you can just click on the figure, move the figure off of the board, and let go, and it just drops into oblivion. If you have problems using Tarski's world, if it's not very intuitive or you don't find it very intuitive, there is help. There's also, by the way, help with submit. Just go to help, right? Where it says help in the Tarski's world window, then click on help. That should take you to a web page, and that web page basically like walks you through Tarski's world and the basics on how to use it. All that said, you may still have some technical difficulties. That's expected, right, in the first couple of weeks of this course. As with problems using the submit program, if you repeatedly try to do this and it just isn't working for you, go ahead, shoot me an email, and I'll try and schedule a time to meet with you, probably by way of Zoom, and through just talking it out and sharing screens and so forth, we will figure out right what's going on and how it is we can solve any problems that have come up. That's all I have for this week. In the meantime, welcome again to class. I cannot emphasize enough, right, the importance of doing the homework. Try to do it. And if you have problems you just can't solve, let me know.